Hello, everyone. Welcome back to day 33 of Coding Every Day. Today is a Tuesday, February 18th at 3:34 p.m. This is my Coding Every Day challenge. So today we're going to be looking at graphs. I'm going to do clone graph today. Okay, so today I'm going to do clone graph. So given a node in a connected undirected graph, return a deep copy of the graph. Okay, so each node in the graph contains an integer value and a list of its neighbors. So that's, that's an adjacency list. Oh, yep, here it is. Okay, so our goal is to return a deep copy of the graph. So a list of nodes where every node has value and neighbors. Okay. Okay, so we'll say clone is an empty list. Or maybe we could do a set. What do we have to return? A list of nodes. Okay, so for now, let's do just a set. So I'm thinking what we'll say is actually, so first let me see what we're working with. So if I'll just return nothing. So if I print node, so is this that's a list of nodes? What if I print node.val? Does that give me an error because the list does not have val? No, it gives me 1. Can I say for x in node, print x? Is it iterable? It should be a list, right? No. So how do I access this adjacency list? Is my question. Or will it? Okay, so the input is not subscriptable, or sorry, iterable. So is it just one node? Node.val. So it just prints 1. Okay, so it wants me to return a list of nodes. Sorry, 1 second. Just have to silence my phone. Okay, so it wants me to return a list of nodes. This will give me a list of integers, which is not what we want either. Yeah. This will give me a list of integers actually. So this should be wrong also. Yeah. So my question is, oh, okay, maybe I have to get its neighbors here. So what happens if I say print node.neighbors? What will this give me? Okay, so we can say for neighbor in node.neighbors print neighbor.val like so. So my output is 2. What if I print neighbor? So there's only 1. Okay, so one. Okay, so I think what we want to do is kind of. Okay, so let's look at this here. So I think we kind of have what we want to do is. So first, I just want to print everything in the graph, so we can access everything in the graph. So I think we'll have stack and visited, which will both contain just the node object itself. Okay, and then we'll say while stack current equals stack.pop. So this is of type node, and then for neighbor in current.neighbors, if neighbor not in visited, then stack.append neighbor and visited.append neighbor, visited.add neighbor, like that. So I just want to print right here this. All right, current.val. 1, 2, 3. Okay, perfect. And can I also get the current.neighbors? Because if I have access to that, then I think I can recreate the graph. This is going to give me a list of neighbors. So I don't think this is what I want, because this is going to be a list of nodes, which is not useful to me. But we can see that 1 has 1 neighbor, 2 has 2 neighbors, and 3 has 1 neighbor. So okay, so we'll make a clone of the graph. So how do we want to store it? We probably just want I'll just call it clone, which will be a list. A list of nodes. Okay, so when we first pop something, we'll say clone dot append we want to create a new node object. So create a node with current value, current.val, and then current.neighbors.copy. Let's just print clone here. Forgot the brace. Let's see what this does. Okay, clone is 3 nodes. So let's return clone and see if that is what we're looking for here. Okay. Your output was copy, but the expected return type is a list of nodes. Is it because here we are copying it? So it's copying the old references. That is probably what is happening. Alternatively, what I could do then, I could say, okay, so like neighbors copy is going to be equal to a list of a new node n.val for n in current.neighbors, like this. Clone.append node of current.val and neighbors copy. Let's see what error this gives us. Okay. All right. So a way to check if something's a deep copy is you can go through both the original and the copy and check the IDs and make sure that they do not equal. So should it be for n? Oh, wait. So node here, we have to create neighbors. Okay. So maybe we can store, because here if we do an empty list, I just want to try this, if this gives me a different error message. I'm not returning clone, right? Same error message. All right, so maybe what I could do instead is make a dictionary. And every time we come across a node, we add it to clone. So maybe what we can say is if currents, so are all the values unique? Okay, this is important. So instead, maybe we could say, okay, so we'll pop this. So we're basically going to traverse through it. And then when we find this, we will add its neighbors. The only thing here is this adjacency list right here. I'm a little confused about. So is it saying 2 and 1 and 1 and 3? All right. Okay, let me print this again. So this prints 1, 2, 3. And let's say prints added neighbor of current to stack. Neighbor.val of current.val. Okay, so we're at 1. We add the neighbor. So we're only given the head of the graph, basically. Given a node. Okay, so we're given one node. And then we add neighbor 2 to the stack, then we pop from that stack, get 2, and then we add neighbor 3, and then pop 3. Okay, so 1, so we're going to create a node 1. So the tricky part is, okay, so if we create a node 1, its neighbors is a node 2. But this also needs neighbors. But I think since we are using values instead, it'll make it a lot more simple. And then at the end, we can just convert the dictionary maybe back into a list of nodes. Okay. So we're going to have clone, which is a dictionary. Okay. So current must not be in the dictionary. So instead of visited, I think we can okay, let's keep it, before we optimize, let's keep it like this. So if clone not in, if current dot val not in clone, then we want to say current dot val, clone of current dot val equals empty list. And then for every neighbor, yeah, sure, if it's not in visited, then we'll say clone of current dot val dot append neighbor dot val, like this. And then let me see what this looks like when I print clone. So 1 is connected to 2, 2 is connected to 3, and 3 is connected to nothing. Okay, so we also want it to go the other way around. So when we get to 2, we want to make sure, so for every neighbor, do we say clone of neighbor dot val? Oh, I understand this output now. Okay. This will give me an error, I think, because it's out of bounds. Yeah. I'll just make clone, for the sake of simplicity, a default dictionary, so I don't have to add all this stuff. From collections, import default dicts. Okay. Hopefully this works. There's no attribute val. Oh, this is supposed to say current.val. All right, making progress slowly but surely. All right, so output, that's good. So our default dict is 1, 2, 2, 1, 3, 3, 2. So this looks good. When I implemented this, I was a bit worried. Can I have a cycle in it? Yeah, I think it can. I don't feel confident in this. So we don't even need that then. So instead of a list, could we have a set of its neighbors? Because the only thing I'm worried about here is that it could add the same neighbor twice. Well, I guess not, because visited. I don't think we need visited. I think we can change this to clone. Okay. So let's assume that visited works for now, and let me write the rest of this program. So how we want it is for every okay, so for item in clone.items, I just want to print item and just make sure I know. So it should be an integer and then a list of integers. Like that. Yes. Okay, so we want to say, so we'll have our result list. We want to say result.append a new node of item 0 and item 1. Like that. Then print result. 3 nodes. Your output was copy. The expected return type. So I was thinking that when I create a node, so I'm thinking that this is a node object, right? So if I say print type, and then I say type of this object, I'm thinking that this is a node object. Type node. But you want optional. Maybe I don't know what optional means. Okay, let me see. So this should also be a list of nodes, right? A list. I honestly don't. I don't know what optional means. I think it's part of the. Am I just supposed to return? Oh, maybe I'm just going to return one node? Whoops, I didn't mean to hit submit. Okay, so it's not giving me a return type error anymore. So that's something. Okay. So, okay, that's something. I kind of had a realization. So this type is actually a single node, not a list of nodes. So I'm used to, like, for instance, like Haskell or maybe even like C# or something. When you have like this syntax, it means a list of type A. Or if you say like ints, that's like a list of integers. So I thought it was a list of nodes, but I should have remembered that this is actually a singular node. All right, so let's look at this error now. So we're getting somewhere. So int object has no attribute val. Neighbors.append. Neighbors. Where do I say that? Okay, I don't think I say this. Okay, so it's in the hidden code, line 128. Neighbor dot val. Okay, so, oh, I see. Okay, I see. So I have integers, but it should be nodes. Okay. So right now a node has a list of integers, but we really need it to be a list of nodes. So I kind of have the same problem. Okay, so we have the correct adjacency list. So if I just get rid of that and I print clone, so we have the correct adjacency list. Okay, so we have, let's draw in blue. Okay, so we have 1, 2. 2 is connected to 1 and 3, and 3 is connected to 2. All right, so how could you do this? Well, you could create a node. It kind of reminds me of like recursion a little bit, and maybe I'll get to that. So, okay, so node we create has 1, and then another node. Two. Yeah, so this is how it's going down. So it's 1 and then a list of nodes, which in this case is just node 2. And then that one has a list of nodes, which is this first node. So I'll call it like N1 that we're creating right now. Okay, so maybe instead what we could do is create every node. So we'll say like N1 equals node with 1 and then just an empty list. And then N2 equals node value 2, empty list, and so on. And N3 equals node 3, empty list. Okay. And then what we do is we say, we go through our list here, and then we say, for every neighbor in node 1, we'll add its corresponding node to that. Okay. So I think the best way to do that, so we'll have, so I'm going to change clone to graph. Okay, so now clone is going to be, or I guess nodes. So nodes is going to be a list of nodes. So I'm going to create a new node with a value I and an empty list from in range, so from 1 to length of graph. All right, so let me print nodes. So this should give us this part. Whoops, this should give us this part here. So if we run that, length of graph +1, and let's say nodes. Okay, so 3 nodes, and then what I want to do is for node in nodes, or I guess I'll say for n in nodes, like that. Then I want to print n.val. So it should give me 1, 2, 3. Okay. All right. Okay. So now what I want to say is for, I suppose we could loop through this, but I'm going to do it. So for n in graph, so the first one is this n. of 1. So we're going to say, and then for neighbor, we'll just say node and neighbor and just overwrite it here. So for neighbor in graph of a node. Okay, so this is a list. Node must be in graph. So for every neighbor, what we want to say is nodes. So we want to access the corresponding node. So nodes at index node -1 dot append neighbor. So this will go through it, and then for every neighbor, we're just going to append the corresponding neighbors to that index. Node object has no attribute append. Okay, so we want, yep, so it's getting us the node object. We want to get neighbors dot append like that. Okay, and now what I want to do is for, I'll just say for I in nodes, print I dot val, and then for n in I dot neighbors, print n dot val. So node equals I dot val, and then we'll say neighbor equals n dot val, like that. Okay, that did not seem to work. Alright. Okay, int object has no attribute val. So why is n oh, neighbor is integer. Oh, okay, so instead of appending an integer, we want to append nodes of neighbor -1. So the node itself. Okay, node 1, neighbor 2, node 2. Okay, this looks perfect. And then I want to return nodes like that. Oh, okay. I want to return one node. One node? Okay, we got one test case. Empty list. Empty. Okay, I don't know. It's so annoying. So, say, all right, so this part is you're given a node that has no neighbors. Okay, so we'll say if not node dot neighbors. So if it has no neighbors, then what do we return? That. Okay, so this should work for test case 2 and not for 3. Okay, it did not work. So we just want to like we want that. We don't want a list though. Okay. In this case, we have none type. So in the case of none type, so if not node, then we should return, what do we return? Just empty list? Or should it be empty node? So it should be a node type, but there is no node. We'll create a blank node. Like that. Not really sure what to do here. So is it none? None neighbors? No. Let me make sure this is getting executed before the print statement, because maybe it's doing this one instead. Yep. Okay, so I guess that means none. Okay, let's see if the other general cases work. All right, we have a problem here. All right, so good, we're making progress. All right, so what did I output? I output this. Okay, so let's draw the graph here. So 1 is connected to 2 and 3. 2 is connected to 1 and 4. 3 is connected to 1 and 4. And 4 is connected to just 3? No, that's my mistake. 3 is connected to 1 and 4. Or sorry, 4 is connected to... Okay. 1 is connected to 2 and 3. 2 is connected to 1 and 4. 3 is connected to 2 and 3. And 4 is connected to 1 and 4. Like this. Okay, so this is the graph. So we have 1, 2, 3 in a ring like that. And then we have 4 here, which is connected to itself, and 3 is connected to itself. So wait, but here it says, I think I have the graph wrong. So 1 is connected to 2 and 3. 2 is connected to 1 and 4, so it's not connected to 3. 2 is connected to 1 and 4. 2 is connected to 1 and 4. Okay, so 1 and 2 are good. And then 3 is connected to... Okay, this part is confusing me. So it says 3 is connected to... could it be one way? So is it one way only? Is it a directed graph? Undirected graph. Okay, so it's an undirected graph. So I'm a little bit confused by this test case, because for 2 it is connected to 1 and 4, but 3 is connected to 2 and 3. And where did it give me the hint right here? So here it says value 1 is connected to 2, value 2 is connected to 1 and 3, and value 3 is connected to 2. So using that logic, it gives me a directed graph. If we assume that this is true, the problem is here it says that node 2 is connected to 1 and 4 only. But then here it says that node 3 is connected to node 2, which is not true based on this. um, maybe they're in a random order. So my output says that node 1. Okay, so my output corresponds with this, which says that 1 is connected to 2 and 3. 2 is connected to 1, right? And that 1, 4. So 3 is connected to 1 and 4. And 4 is connected to 3. So this looks like a real graph to me, but obviously it's wrong. So there must be something that I am not understanding. So let me add this as a test case first of all. And then let me see in the depth first search how this looks. So the first node we get, let me print node here. So the first node we get is 1. Okay, so here let me say current.val popped like this. Okay, so 1 is popped, and then we add 2. And then we pop 2, add 3, and pop 3. And that's it. So we never pop 4. Okay, so let me print all the neighbors. So we'll say neighbor.val equals like that. Okay, a lot of stuff going on. So we start with 1, neighbor.val equals 2. So according to this, the only neighbor here is 2. Oh, I'm looking at the wrong test case. That would explain it. Okay. So neighbor 2 and neighbor 3 get added to the stack. Okay, so we have our stack 2 and 3. And then we pop 3, and then add neighbors 1. So neighbors 1 and 4, but only 4 gets added to the stack. That makes sense. Current val 4 popped. So we pop 4 from the stack. The neighbors are 2 and 3. Okay, so here it says that I'm going to try printing this here. So I'll say n.val for n in current.neighbors. Okay, so let's see what this says, because maybe I'm just building the graph wrong, I guess. That looks good. Okay, so it's saying All right, so 2, 3, 1, 4, 2, 3, 1, 4. So it looks like okay. So this is interesting because we have 2, 3, 1, 4, 2, 3, 1, 4. So value 1 has neighbors 2, 3. That adds up. So this is where it's tricky because current val 3 has neighbors 1, 4. But 3 is here. So their output is not. Okay, so according to this adjacency list, it suggests that so 1 is connected to 2 and 3. 2, so then 3 is connected to 1 and 4. 4 is connected to 2 and 3. And 2 is connected to 1 and 4. So that's what this suggests here. But I thought it was I thought the output, the index had to line up. Maybe it doesn't, but then how do you know the order? Or does it not matter? So there's two problems going on. So first of all, 2 of our nodes are missing all right. So let's get this a little bit more organized here. So we're going to print something and then we'll say end equals just a space. And here we'll say end equals a space like this. I do have to go soon, so hopefully. So here we have 1 is 2, 3. That's correct. 3 is 1, 4. That's correct. 2 is 1. But it should also be 3. So let's print our graph and see if our graph is working or if it's this part down here. So like this. Our graph says, so our graph is wrong. Our graph doesn't have 4 in it. So I think it has to do with this part here. Yeah, that's probably what's causing it. Wait. I was in the wrong tab. Okay, so our graph is wrong. Okay, so that's good because that means it's just something here. I think it's just this. My instinct was that something was wrong with this part here. So ideally what we could just do is so for neighbor and current dot neighbors, if neighbor not in graph of currents, then we can just add it and say graph of currents dot append neighbor like this. But the problem with this would be it's linear scan lookup. Okay, so it's supposed to be values. If current. Okay, so now it's getting accepted. And it just fixed it. Okay, so the only thing that was wrong was my graph. So all that. Probably should have checked that first, but that's okay. We learn. Okay, so this part all is fine. And then let's look at the time complexity. Okay, so it should be done in one depth first search. Or any number of depth first searches. So this part is actually fine. That's v plus e, I believe. Because for every vertex will be v times e, right? Well, this is for every vertex. And then all of the edges associated with that vertex. So this might be v plus e. I need a little bit to review like the time complexity of depth first search and if this is v plus e, because maybe the way graph theory works out, it's not v times e, because you know that not all nodes can have all edges. Okay. So first thing, okay, so we have a solution. Wait, let me see if it works. Okay, so it works, but that's with a heavy asterisk. So the heavy asterisk. Okay, so I'm going to get rid of all of this stuff for now. I'll just put this down here. Probably going to want that. All right, so first thing we should do is we'll say DFS to build adjacency list graph. I'll just say graph. All right, so DFS to build graph. What happens if we just get rid of this and say this? Okay, so it works. Why? Oh, yeah, that makes sense. So it's never, so I was thinking we don't want to add the same value twice, but that's not possible because the only time we would add the value is when we explore a node, when we explore that node, and we only explore every node once because of visited. Okay, so the second thing I want to do is get rid of visited, and I think what I can do is just okay. So I have a default dict, so I'm not really sure how this is going to work. Okay, let's see if this works. Okay, that's a infinite loop. I'm thinking basically what we can do is get rid of visited and then just only use the graph data structure, the dictionary. I don't know if so let me say neighbor. Oh, well, maybe we'd have to say if neighbor.val not in graph instead, because graph is values. Does that work? No. So when do we add it to the graph? When do we add something to the graph? We never add anything to the graph because it's a default dict, right? So the default dict is making it a little confused. or making me a little confused. So if we took that away, we would have to say here if current.val not in graph. Okay, could we say this? Wrong answer. Is it because of this, or is it because of what I just added? Okay, so it's because of this. So we add it to the graph. Could we say here instead? Well, we want to check if neighbor is not visited. So we're okay. So the problem is, could we say here if neighbor.val not in graph, then neighbor graph of neighbor.val equals empty list. Let me make sure this doesn't ruin anything. Okay, so if we can do this, then we can say stack.append neighbor like that, and then we can get rid of this, perchance. Yep. Okay. Does that work? Okay, rate limit exceeded. We gotta chill out for a sec, guys. All right, so another thing too, I could just add both connections here. I don't know if that will improve it. I guess it's not technically needed, but so the reason I would do something like this, okay, so that doesn't work. Did I spell something wrong? No, just wrong answer. Okay. So I will not do that then. I don't. Oh, okay. So this part will actually cause redundancy. Like it will append things twice. So we want to make sure everything gets appended once. Okay, so this. Okay. So now we've just replaced graph with the visited set here. So we don't need visited anymore. We don't need any of this. Don't need that. Okay, so this is part one, is DFS to build the graph. And then part two is using graph construct outputs list. Or it's not really an output list. Construct list of nodes. Okay, so this part, I think these are both V plus E actually. And I don't need that. I'm not sure about this part. the nested for loop here. I think it is V plus E. Because it's very similar. It actually is very similar. So I know depth first search is V plus E, and this is the depth first search. So in this case, basically with the stack, that means we're popping for every node. And then for every node, we're looking at all of its neighbors. And that is exactly what we're doing here. So if this is V plus E, because it's a depth first search, then this must also be V plus E, which means the whole thing is V plus E. So I think this is the correct time complexity as well. So let me just submit that final one. And it's perfect. Okay, so there we have it. Just about an hour in. And I'm very happy with that one. I kind of muscled through it. And was confused about this return type. Admittedly, a lot of my confusions were because I didn't read the problem carefully. For instance, like I kind of missed this part, and then I missed that you're given. Oh, I had to revisit this part with the undirected and given a node in a connected graph. That was something that I wish I read instead of thinking it was a list of nodes because of this notation. Yeah, so that's clone graph. Thank you guys very much for watching. Today was day 33. Like I said yesterday, the questions are getting pretty challenging for me, but that's good to learn. And for some of the videos, I might end up just doing it for an hour and then, kind of giving up and just, looking at the solution. But I think that's the best way to learn, is not get too caught up on any one problem. So I'm going to keep going, and I'll see you guys tomorrow for day 34.